How would you find the remainder when a of x, which is given by this cubic here, is divided by p of x, which is a linear function here? In case you haven't seen this notation before, I'll just briefly explain it. So this is the same thing as if you say y equals 5x cubed minus 6x squared plus x minus 1, right? It's the same thing. It's also the same thing as if you say a equals all this, and that's what we've done here. We've just called it a instead of y. And to make it clear what the variable is, right? We know what the variable is. It's pretty obvious. It's just x. X is the thing that changes. But in function notation, which is what this is called, you always have to be really explicit, right? And for that reason, instead of writing just a, we write a of x, just to make it 100% clear that the variable is x, right? So that's a quick recap of this sort of notation if you haven't seen it before, because we're going to be needing it in this lesson. So how would we go about solving this? Well, let's use polynomial long division. So we're going to have x minus 2 on the left here, and on the right we're going to have 5x cubed minus 6x squared plus x minus 1. Okay, awesome. We know how to do this. Straightforward. We need to multiply x with 5x squared to get this term here. When we multiply 5x squared by x minus 2, we get 5x squared minus 10x squared. Subtract the whole thing, we're left with 4x squared. This plus x comes down the bottom. We need to multiply x by 4x to get 4x squared. We put a 4x there. 4x times x minus 2 is 4x squared minus 8x. Subtract the 2. We're left with 9x. The minus 1 comes down the bottom. We have a 9 here because we need to do 9 times x to get 9x. If we do 9 times x minus 2, we get 9x minus 18. Subtract the 2, and we're left with our answer, which is 17. Okay, so that wasn't too hard. Now I'm going to give you 20 more questions of exactly the same format. How would you like to do that? Do you want to do 20 polynomial long divisions? I didn't think so. This is why we're going to introduce a theorem called the remainder theorem. So what is the remainder theorem? Well, this is a theorem that states that if we have any polynomial at all, whether it's a quadratic, a cubic, or it could even be to the degree 100, right? If we have any polynomial a of x, and we divide it by a linear function x minus k, then our remainder is a of k. Okay, what this means, in case, again, if you're not familiar with function notation, this is a when you sub in k. This is just a shorthand way of writing a when you sub in k. In our previous question, we had this cubic here divided by x minus 2. So what this tells us is that the remainder should be a of 2, or in other words, it should be the value of this when we sub in 2. Okay, let's try and compute that and see if it matches what we got before. So if we sub in 2, we're going to get 5 of 2 cubed, which is going to be 8, okay, minus 6 times 2 to the 2 squared, which is 4, plus 2 minus 1, okay. This becomes 40 minus 24, 2 minus 1 is 1. That is 16 plus 1, which is 17. 17 is exactly what we had before. If you recall what we did when we used polynomial long division, we got a 17 as well. So this sort of gives us an intuitive understanding that the remainder theorem looks correct. Let's now prove this for the general case when we have a of x divided by p of x. Now, this only works when p of x is a linear function, right? So I'm going to rewrite this as a of x divided by x minus k, right? That's the general case, and that's what was stated in the remainder theorem. So the remainder theorem says that this should be equal to, just to remind you, the remainder should be equal to a of k. Okay, we're going to prove that now. If we were to use polynomial long division, it would look something like this. We'd have x minus k here. We would have a of x here. Okay, now we would continue to solve this and we would get some remainder, r. Okay, so it's going to be a constant r. We don't know what that is. And up the top here, we'd get another polynomial, and it would be our quotient. So let's call it q of x. Okay, you can call it whatever you want. Before I go into this, I want to go through a similar case, but using something you're more familiar with. Okay, so let's say instead of dividing polynomials, we were simply doing a plain old 567, right, divided by 4. Now this is the same division that we did in our polynomial long divisions video when we were first introducing this concept. Okay, so we're going to have our division sign there. We've got a 4, and then we've got 567. Okay, and I'm not going to go through the calculation, but we saw in that video that the remainder was 3, right? The remainder was 3. And the quotient was 141. Okay, now another way we could write 567 is by saying 567 is equal to 4 times 141. Is that all? What do we need to add? We need to add 3. Okay, does that make sense? 567 divided by 4 gives us 141 with a remainder of 3. So if we do 141 times 4 plus 3, we're going to get 567. Okay, now the same thing applies to polynomials. So a of x, right, that's the same thing as x minus k times q of x, whatever q of x is. We don't know what it is, but it's just going to be some polynomial, right, plus the remainder r. What happens when we sub in k, when we take a of k? Okay, remember what we're doing here is wherever there's an x, we replace with k. Okay, so this becomes k minus k times q of k. Now q of k will just be the value of q when we sub in k. Okay, and r just stays the same. What does that equal? You might see where this is going. This is 0. K minus k is just 0 times q of x plus r. And this whole thing just becomes 0, so we're left with r by itself. Okay, in other words, what we've got is that a of k is equal to r, our remainder. And that is exactly what the remainder theorem stated. So we've proved it. Okay, we've proved that if you divide a of x by some linear function x minus k, the remainder is just going to be a of k. You just have to sub in k into a, which is the equation you started off with. In our first example, k was equal to 2 because we were dividing by x minus 2. That's why the remainder is just a of 2, or in other words, subbing 2 into the function that we're dividing. This is a very powerful theorem that is essential to factorizing cubics and therefore finding the x-intercepts of cubics.